A single linear operator can be represented by many different matrices, depending on the basis we choose. To find the properties that remain constant across all these representations, we look for a sequence of polynomials, called invariant factors. These polynomials serve as the components for the rational canonical form of a matrix. By identifying them, we can determine the most direct way to express the operator's underlying structure. This sequence follows a strict rule. Each polynomial must divide the one that follows it. In this chain, f1 divides f2, which divides every subsequent term until we reach the final factor, fk. There is a direct link between these factors and the matrix itself. Each polynomial, fi, determines a companion matrix, a specific square block on the diagonal. When we group these blocks together, they form the rational canonical form. This sequence of polynomials is unique to the linear operator. By finding these factors, we can distinguish one transformation from another and construct its canonical matrix representation. The process begins with the matrix xi minus a. This is formed by taking the variable x times the identity matrix and subtracting the original matrix a. In this matrix, the entries are not just scalars, but polynomials. We can manipulate these entries using row operations, similar to numerical matrices, but we must account for polynomial division and remainders. This is the xi minus a matrix for a general companion matrix. The variable x appears along the main diagonal, with negative ones directly below them. We eliminate the x terms on the diagonal by adding x times a lower row to the row above it. Repeating this from the bottom up clears the diagonal entries, accumulating polynomial terms in the top right. Once complete, the characteristic polynomial p of x is isolated in the final entry. The remaining diagonal reduces to a series of ones. In the case of a companion matrix, this reduction shows that there is only one non-trivial invariant factor, and it is exactly equal to the characteristic polynomial. Manual row reduction becomes difficult to track as matrices grow larger or contain more complex polynomial entries. For these cases, we use a more structured approach. We look for determinantal divisors, labeled delta k. To find delta k, we calculate the determinants of every possible k by k submatrix within xi minus a. The greatest common divisor of all these determinants is our kth divisor. These divisors directly reveal the invariant factors. The kth factor, f of k, is the result of dividing the kth determinantal divisor by the one that preceded it. For a simple 2 by 2 matrix, delta 1 is just the greatest common divisor of the 4 individual entries in xi minus a. Calculating every possible minor for a large matrix is computationally heavy, but Theorem 9 provides a shortcut. It states that elementary row and column operations do not change these determinantal divisors. This invariance means we can use row and column operations to simplify the entries of the xi minus a matrix before we ever begin calculating the minors, making the final computation manageable. These invariant factors connect the algebraic calculations back to the fundamental geometry of vector spaces described by Hoffman and Kunze. Each invariant factor f of x we compute represents the operator's behavior within a specific cyclic subspace. The decomposition of the entire vector space is mirrored in the sequence of these polynomials. The divisors also define the operator's primary polynomials. The final factor in the chain, fk, is the minimal polynomial. If we multiply every factor in the sequence together, the product is the characteristic polynomial. This ensures that every square matrix has exactly one set of invariant factors, providing a consistent result regardless of whether we use row reduction or determinantal divisors. Computing these factors is the final step in classifying a linear operator. It provides the necessary data to determine the rational canonical form and understand the structural limits of any linear transformation.